Okay, here we go. And a 1, a 2, a 1, 2.
Welcome to the Beyond the Expected podcast. Professor Abhay Deshpande, thank you so much for joining us today. So why don't you start off by telling us how you became interested in understanding a small problem, the origins of the universe?
Yeah, well, it's a small problem, which remains to be solved for more than 100 years. Well, when I was very young, I was not following physics as in a textbook way, but I did ask a lot of questions. And one of the questions I remember when I was in high school that I asked was, the magnets align themselves with north and south. What happens if we walk with the magnet to the North Pole? Shouldn't the south and the magnet and the North Pole are under your foot, and then the magnet should bend? So for a fourth degree grade student, this was a question which would have been solved by a simple answer, but I was punished for it by my science teacher. And fortunately, my parents were open enough that they took me to another more serious physicist, and he encouraged me to do all kinds of ask these kind of questions. And he gave me a book called The First 3 Minutes by Steven Weinberg. And Weinberg is a Nobel Prize winner, and he talked about how the evolution of the universe might have happened. And that I remember very vividly, that book. And that was the clinching part as to starting from the Big Bang, we knew that existed. How did the energy come about? How did the particles form? How did the nuclei form? And it's fascinating to me now, and I remember those months.
That set you on
fire. That really
fire.
set me on that,
Right.
and in that direction.
So you, of course, have been involved for a couple of decades now in not only pursuing this research, but in leading a major effort to create a whole new device to explore these deep questions about the origins of the universe. So why don't you tell us a bit about this new instrument that will become part of the Brookhaven National Laboratory campus nearby Stony Brook, and how this Electron Ion Collider, as it's called, how it will be useful in finding the answers you're looking for.
Yeah, so as I mentioned to you that we need to understand how protons were formed. We know for about 50 years that the protons are made up of quarks and gluons. But we don't know how these quarks and gluons bind together to form the exact proton that we love in this nature. It has a specific spin, it has a specific mass. How these quarks and gluons, which are themselves massless, almost massless, come up with this mass of the proton. Because if you just barely calculate their mass, it's 1% of the total mass of the proton.
And the protons compose the atoms that create all the things we
exactly,
see. Exactly,
everything. They're at the heart of the atom inside the nucleus, and everything we see in nature is made up of nuclei of different kind. Everything that we see in the universe is made up of that. So the question then comes as to how do we look inside the proton? And if you have an object that you want to look inside, you want to have a probe which does not have a structure, that when you collide that probe with the target, which is in this case is a proton, everything that comes out of that collision has to be from the target that you want to study. And nature gives us a beautiful instrument called the electron. It is a fundamental particle. It has no structure. So once you bang something with the electron, the only thing that comes out has to come from the remnants of the proton. So that's the clean way of entering the proton and looking what inside is. Over the last 10 years or so, 15 years or so, a new technique has been developed where you can actually go inside the proton without breaking the proton. It's like taking an MRI of a proton. And that's something that tells you what's going on inside the proton without too much disturbing it. In fact, in my colloquia, I actually call it non-violent collision. Non-violent collisions, for me, growing up in India, is from associates with Gandhi. And so the non-violent movement, I call them Gandhian collisions sometimes, just to explain what it is. It doesn't break anything, and we want to go inside nuclei as well as protons. So that's what the Electron Ion Collider will do. The electron is the probe, the proton, nuclei that we will have in the other colliding ring of this collider will be the targets, and we will explore how these quarks and gluons actually make up not only the protons, but the neutrons and all the nuclei.
But this new installation, the collider, is somehow uniquely capable of doing this? Why is that? How is that so?
So to understand all these properties of the proton or the neutron or the nuclei, we need a few controls in the experiments. One is we need to control the spin of the proton. Proton inherently has a property called spin. It's like the inherent angular momentum. The quarks have it of their own. The gluons have it of their own. But when you sum up the angular momenta of the quarks and gluons, magically it doesn't match up to the proton spin. It's one of the puzzles that we're trying to solve. But to study this under a controlled condition, we need to control the spin. At the moment, the only place in the world you can actually do this is the Relativistic Heavy Ion Collider that already exists at Brookhaven. So that's one of the important things that we need in our future experiments. So that's one thing. The other thing is we want to understand how the gluons that bind the quarks together, how do they interact? What role do they play in binding this? Not just the protons, but also the nuclei. And again, the Relativistic Heavy Ion Collider that exists currently actually has all the nuclei in the collider ring. We have done experiments with it. What we don't have is this electron, the precise probe that we're looking for. So far, we are doing collisions with protons and protons or nucleus and nucleus to understand what's going on. But now we need to get to the next level of precision. And that's what the Electron Ion Collider will do at Brookhaven Lab.
And so how will the project take shape? When will construction begin?
So what we were delighted to see now is we just got the CD0, which was the project approval from the Department of Energy, which means that now they can start spending money on this project. So they have asked for a profile of what would be the construction cost, and then the timelines, and Brookhaven has provided them, and they have looked at it, reviewed it, and they have something in mind that will allow us to plan it out. So they will start helping us build the collider on the machine side, and we expect that about 10 years from now, 2030 or so, we will have the first collisions. During the same time, the people who want to do the science on the experimental side, like me, we want to start building the detectors. Once the collisions happen, you have to put a detector around it to see what comes out of such collisions.
Record the
Exactly,
events.
record them, and then we can analyze them and see where these particles are coming from. So from what we see in our detectors, we can project back and see what happened in the collision itself, which is really what we're trying to understand. And from there, we can check our theories of the understandings that we have. If we come up with observables and things that we see are consistent with our theory, we say, okay, what we understand as the fundamental theory is right. If it is not, then we have learned something. So then we modify our theory. So this process keeps on going.
Right. And just to those who are watching and listening, the scale of this project, how big is this instrument?
Physically, it's a 3.8 kilometers or 2.4 miles perimeter of this machine. As I was telling someone, if you fly out of Islip Airport at Long Island or the local New York airports and the flight is not too high, you can actually see it. You can see on the left-hand side going east that there is a big circle on the ground.
Yeah.
And that's the Electron Ion Collider.
And so this is also a massive construction project. There's going to be a lot of work to be done.
There is a lot of construction. However, one of the tricks that we have tried to do is because we are going to use the existing beams of RHIC, the civil construction of this project, particularly at Brookhaven, is not a large project. So what we plan to do is to construct the electron beam facility inside the same tunnel as that of
the Relativistic Heavy Ion Collider
exactly.
that already
exists. And there are two rings there we want to make, and there is ample space for the third electron ring. So what we are trying to do is to install the electron ring in the same tunnel and use one of the existing rings to have collisions. So that way we don't have a lot more new construction.
Are there other uses for this resource? You've detailed the specific issues of looking within the nucleus, looking within the proton.
Yes.
Are there other uses for a machine like this?
Because we put a lot of constraints and the demands on the accelerator, that is giving us these collisions from the physics side. What do you want to do physics? And then to do that physics, what are the parameters of the machine? That really is pushing the accelerator parameters to really state of the art or beyond what we have, what we have built so far. 100 times better than the previous machine, 1,000 times better in luminosity than a previous machine. So that's really daunting, which is pushing the accelerator technology frontier in ways that people had not imagined just 20 years ago. So what that means is that we know that these accelerator technologies are going to be useful not only for the physics that we do, but they are useful in medicine. Some of the radiation therapies come up with it. We are producing better beams, more focused, narrow beams, or beams for precision radiation therapy treatment. Right. For example, we are going to produce beams which are used for silicon technology. Some of the detectors technologies that we will develop will be used for national security, as well as some of the fast electronics we'll build. People will play games with it, extremely fast games. That's where that's where the growth is in industry. But I think most important, I think this is going to create a opportunity for scientists, young and not so young, to come and work on this frontier technology here on Long Island.
And I heard you say earlier, you said 20 to 30 years. So this is a generation or more of work.
It takes a generation. It takes a village. It takes a nation to build such a collider. And it is true. People have tried to build this for 20 years, and fortunately, now we are succeeding. And 10 years to construct it, and there will be another 20 years of physics.
So this may be a difficult question to answer, but so once the facility is up and running and you're doing your science, how long does it last? Or is that impossible to predict?
No, it's typically we will exhaust the parameters in about 20 years. So typically these high energy large colliders have a lifetime of about 20 years. So RHIC started in 2000 and 2001, and now it is coming naturally to the end of its science. There are 4 or 5 years remaining, and we will extract science out of that. Then there will be a transition to the Electron Ion Collider. I expect that after that, there will be another 20 years or so of science to be done.
Right. So almost a half century of effort and then science around it.
Absolutely. It's a patience game.
Yes, and that actually raises another interesting question about you. Talk about being patient. I mean, you've invested. You're a young man, but you've invested, several decades of your life in this agenda. So, how do you do that? What is that like?
Well, to be very honest, I mean, the ideas for such a collider came first in the late 1990s when I was a postdoc, and I was not trying to build this machine here. I was already working at a machine in Hamburg, and I wanted to modify that existing machine to do what I want to do with polarization and the spin control and the nuclei. And I was trying to save money at that time. There was very small upgrades of the existing machine. And it didn't work out because the management there wanted to go to bigger projects. I was asking for $30 million, and there were $2 billion projects at that time, completely different. And that just did not go well. The Germans wanted to go in a particular direction. But at the same time, when these ideas were being developed, I had the opportunity to interact with some of the world's best scientists, absolutely greatest scientists in this field, just happened to be around me at that time, which my experiments at CERN. And I learned a lot from them in general for my day-to-day experiments. However, one of the things that was impressed upon me by a Nobel laureate, Jack Steinberger, who was visiting me and was asking me questions about this project, in 1997, he said, why do you want to do this? And so I gave him a half-an-hour spiel as to what I wanted to do. And then he basically told me, this is good science. No matter how long does it take, you need to pursue it. It was an impressive comment from such a, prestigious, accomplished person for a young postdoc. And I took that to heart. I mean, if he thinks that this is good science, it's worth pursuing. Yeah. Now, truth be told, at that time I was naive. When I proposed this at Brookhaven, the initial time squares for that were about 10 years. I thought that we would be done in 2007. As things go, we realized the difficulties in technologies and the physics that was developing in parallel with it. So over time, I have seen this project grow, not just because of me, in fact, because of a lot more people like the idea They came in, they came up with new ideas, and they made this project better.
And you've touched on something. So you've mentioned Brookhaven, and of course your work in Europe. CERN is the European Center for Physics Research. So this is really a global community.
Effort. It's a global effort. People have tried to answer these questions in all parts of the world using the technologies that they had. And now they realize that the only way to solve this problem is to use what we are trying to do. And that's why this project now has 1,000 users around the world, with 30 countries participating and 180 institutions who are now parts of it. This morning, we crossed the 1,000 mark. This morning,
marvelous.
So it's not. As I said, it's really takes a village, or a village in the terms of
world
its
village.
A world village.
Just focusing locally, just for one more moment.
Yes.
So looking at Stony Brook, what does this mean for faculty like you at Stony Brook and your students, graduate students and undergraduates?
Opportunity. I mean, being there is very important. In every place, if you are present in person, it's very important. To be at Brookhaven at an experiment, if you're a faculty or a graduate student or an undergraduate student, even I have lots of undergraduate students working with me on my research projects, it is just much, much easier to get exposed to the technologies, the frontier experiences that you can get by getting involved. So this is going to be a tremendous deal for a university like us. There's no question about it.
So you mentioned experiments. So how long does it take to run an experiment in a collider like this?
Yeah, typically the experiments get built over 5 to 10 years. Wow. Then they go into the collider interaction region. And then every year we get a budget from the DOE to operate the machine. Typically we get about 4 months to 6 months of operating time.
Runtime.
And then once we get it, we run 27 hours a day, 7 days a week, and we run shifts completely for that as much as we
Gathering as much data as you possibly can.
Yeah. And then we go into the sleep mode where we start fixing things that go wrong or thinking about improving things for the future, the next run, taking rest a little bit over the next few months to recuperate. And so I think this cycle goes, and that's when I said that about 15 to 20 years of operation goes into it. Not all runs are the same. I mean, because of the versatility that we need for the science program, we need polarized protons, we need unpolarized protons, we need polarized electrons, we need nuclei, we need to change the energy of the nuclei. We have to go in one experiment to the other just by changing some things in the controlled experiment. So all that, again, you look at the whole program, every year we will have 2 or 3 modes of operation. And there will be a few modes before we actually start producing good results. So it's a annual planning.
And with the results, you generate enormous amounts of data, I'm sure. And I mean, this could generate literally hundreds of papers, right? This could go on for years.
Yes.
Just digesting all the data.
Yeah, typically a good running experiment. Now I can tell you from our current experience, my current operating experiment, Phoenix, or the STAR detector collaboration here, we produce about 12 to 15 papers a year, which is a collaborative effort, of course, but that's typically what comes out when the project is mature and we are ready to produce science.
So I have to ask you, you're wearing your Stony Brook red shirt, which I'm very pleased to see, but I also noticed you're wearing a very distinctive tie. Maybe you could tell us a little bit about that.
Well, this is a tie that was given to me by Sam Aronson, who was the ex-director of Brookhaven, when I left RHIC Biennial Research Center to come to Stony Brook as a faculty. And this was my parting gift. It's a tie that is made up based on the calculations, pictures of the calculations that they found in one of the rooms at Brookhaven that eventually got the Nobel Prize for T.D. Lee, so this was a special tie. Yang and Lee, Professor Yang.
Yes, C and Yang. That's right.
Lee, yeah.
So
this is a parity violating calculation that they made.
Right, and
don't ask me to solve that.
I was going to say it would require a special person to read this tie and to understand completely what it has to say.
Yes.
So one final question: if you could speak to your younger self, Abhay Deshpande in high school,
yes,
given what you now know,
yes,
what would you tell him?
I would say just follow your heart and don't be shy of asking questions no matter what. And once you know those right questions, talk to seniors, talk to good people who are advising you, and then formulate that strategy. as to what do you really want to do in life, and I think then just follow it no matter what. I think that's just keep at it.
Devoted passion
Yeah.
gets you where you need to be.
Yeah.
Well, Professor Abhay Deshpande, it's been fascinating learning more from you about the Electron Ion Collider, and I know I speak for the entire community, both at the university but here on Long Island. Congratulations
thank you.
on bringing this marvelous new project to fruition
you.
at Brookhaven and
And
for all of the scientific community around the world.
Yes, but I must say that the proximity of the university has helped, and the university has helped tremendously in getting where we are right now. Personally, for me, our groups and our research. So thank you very much.
Thank you so much.